Hello, ClinPath Ninjas. Today we're going to review the CBC erythrocyte indices reported by most analyzers. The erythrocytes are described by a collection of values that reflect the quantity of red blood cells. So that includes the red blood cell count, the hemoglobin concentration, and the hematocrit. Values that describe their size, the mean cell volume and the red blood cell distribution width, both of which are depicted on a red blood cell histogram, and the amount of hemoglobin the cells contain, which includes the mean cell hemoglobin and the mean cell hemoglobin concentration. These values are a mix of direct measurements and calculations. So the red cell count and the mean cell volume are determined as individuals are counted, and the hemoglobin concentration is measured through spectrophotometry after red blood cells are lysed. We're going to start at the top of this list and go through these one at a time. First up, the red blood cell or erythrocyte concentration. To enumerate the erythrocytes, the analyzers take a known volume of sample, dilute it in an isotonic solution, and then directly count the number of erythrocytes. This is then reported as a number of cells per unit volume. In this case, 10 to the 6th per microliter or 10 to the 9th per liter. As we know, the red blood cells are the most numerous formed element in the blood and are reported out in the millions. When the erythrocyte count is below the reference interval, we use the term anemia. When they are above the reference interval, we use the term polycythemia. The second means of evaluating the quantity of erythrocytes is by measuring the hemoglobin concentration. As I mentioned before, the hemoglobin concentration is measured using spectrophotometry. The erythrocytes are lysed and the red blood cells release their hemoglobin. The analyzer then determines the mass of hemoglobin present within a specific volume, and it's reported out as a concentration of grams of hemoglobin per deciliter. We interpret this result the same way we do the PCV, the hematocrit, and the red cell concentration. If it's increased, then it's polycythemia. If it's decreased, then it's anemia. The last way the quantity of red cells is reported is the hematocrit. The hematocrit is the analyzer's way of reporting the PCV, and the hematocrit and the PCV should be within 3% of each other. The hematocrit is calculated as the red blood cell concentration multiplied by the mean cell volume. This is then divided by 10 as a unit conversion factor. If we think about it, this calculation makes a lot of sense. When we're visually measuring a packed cell volume, we can imagine how the number of red blood cells and how big or small those cells are will impact where that dividing line between the red blood cells and the buffy coat and plasma will appear. The bottom line is we interpret the PCV, the hematocrit, the red cell concentration, and the hemoglobin concentration the same way. And all of these values should be changing proportionally in our patient. Moving on to measuring the erythrocyte size. At the same time as the analyzer is counting the number of red blood cells, it's also measuring the volume of each erythrocyte. And this gives us an indication of their size. The analyzer then takes all those measurements and provides an average, or mean, of the erythrocyte volume. The terminology used to describe the mean cell volume is as follows. If the mean cell volume falls within the reference interval, we call it normocytic. If it falls above the reference interval, we call it macrocytic, and below the reference interval, we call it microcytic. And this terminology translates directly to our descriptions of erythrocyte size on blood smears. The mean cell volume is visually depicted on the erythrocyte histogram, and this is how histograms are set up. Across the x-axis is size, in this case red blood cell volume measured in femtoliters. It goes from smallest on the left to the largest on the right. On the y-axis is the number of those cells. And you'll see here that there is this black vertical line dropped on the left side of the curve, and it's called the discriminator. It represents where the analyzer has determined that the red blood cells end and the platelets begin. So to the left of the discriminator are platelets, and to the right are the erythrocytes. And the platelets then get their own histogram. The curve itself represents the distribution of red blood cell size, and you'll note that it appears as a bell curve. So the smallest erythrocytes are on the left, and the largest ones are over here on the right. And the extremes are in the lowest numbers. And you'll see that the red cells cluster around one size, and the middle of this peak of the curve represents the mean cell volume. Which brings us to the other descriptor of red blood cell size, the RDW, or the red blood cell distribution width, also measured in femtoliters. The RDW describes the variation in erythrocyte size, or anisocytosis, and its calculation is derived from the red cell histogram. As its name suggests, it reflects the width of the curve. The RDW calculation is based on the standard deviation of the curve, so the tails at each extreme are excluded. The wider the curve, or the higher the RDW, the more red blood cell size variation is present. Next up is evaluating the amount of hemoglobin in each cell. The mean cell hemoglobin is a calculation that represents the average amount of hemoglobin in each cell. It's considered a redundant measurement and not particularly useful, so most of the time we just ignore it. And now you know. The mean cell hemoglobin concentration, on the other hand, gets a bit more attention. It's a calculation where the hemoglobin is divided into the hematocrit and then multiplied by 100 as a conversion. The analyzer uses the calculated hematocrit, and the PCV, which is basically the equivalent of the hematocrit, can also be used. And here's a fun fact. In most species, the hemoglobin concentration is about 1/3 of the hematocrit. So the reference interval for the MCHC hovers around 33 grams per dil. The exception is our camelids. They have a higher concentration of hemoglobin per erythrocyte, and they tend to hover in the 41 to 45 grams per dil range. As for terminology, when the MCHC is within the reference interval, we call it normochromic. When it is less than the reference interval, it's called hypochromic. And when it's greater than the reference interval, it's called artifact. Remember, there are only so many seats for hemoglobin on the red cell bus, so anytime there's an increase, it's artifact. So what does it mean when the MCHC is decreased? There are two big differentials, the first being an anemia with a significant regenerative response. Usually this requires a presence of greater than 20% immature erythrocytes to see a shift in the MCHC. The other differential is a severe iron deficiency, when the red cells are microcytic and there's so little iron left that they have significantly depleted amounts of hemoglobin. In both cases, the MCHC is not particularly sensitive in picking up these changes, which is why reticulocyte counts and visually examining blood smears for polychromasia or hypochromasia are important. An increased MCHC is due to artifact. When you see an increased MCHC, you want to look for a few things. To remember these, look to the calculation. The hemoglobin is in the numerator, so when it is overestimated, it will increase the MCHC. Keep in mind that the hemoglobin is measured by spectrophotometry, so when turbidity is present in the sample, it will also falsely increase the hemoglobin. The hematocrit is in the denominator, so when it is underestimated, it will also increase the MCHC. Examples of things that increase the MCHC are hemolysis, where hemoglobin is released from erythrocytes and already present in higher concentrations, lipemia, which is quite turbid, and Heinz bodies, where the precipitated hemoglobin can interfere with the spectrophotometer. For the hematocrit, the classic example is agglutination, where agglutinated erythrocytes are so large they aren't included in the red cell count and thereby decrease the hematocrit. The only topic not included in this presentation is reticulocytes. I'm going to refer you to Dr. Thrall's notes for this section. Also, she has a few nice examples of red cell histograms in her notes, so be sure and check those out too.